Welcome to our lesson 2 on pulley system. Lesson 2. I've tried to maintain this data so that I use it. The only part I will not need, maybe I'll be using to explain, is this part. So we have this, I can rub now, there. Okay, I can use that space now to explain. Okay, now let us look at what I argued the last time. Here, I want you to get the concept of the lower pulley. It is always there. The lower pulley is there and it will move. We have to give part of our work done there. The work that we do to overcome friction and to lift the lower pulley is called non-useful work. I don't want to say useless work. Okay, so there is the load that we want to lift. The work I do to it for it to be lifted is called useful work. Okay, the other one, the work done against friction and lifting the lower pulley, we can also call it energy lost. Energy lost, there is nothing good about it. So remember, energy lost is work done against friction and overcoming or lifting the lower pulley. Get it right. So there is useful work and there is energy lost. Energy and work are the same SI unit, joule. Okay? Okay? Work is done when energy is transferred. So work in joules, energy in joules. Okay? Now let us come here. I want to explain something on this part so that you understand. Look at the trend. The energy we put is all that we have. It is 100%. Now suppose energy to lift the load is 100% and everything has gone there. Then it means energy to lift the lower pulley will be 0 because this and this must add up to 100%. You will be contradicting yourself because already you have said the lower pulley has a weight of 100 newtons. So this is not viable. Okay? There is a limit to it. We can't. Then reverse. Suppose I put 100%, all that I have, to the energy to lift the lower pulley. Nothing will remain to lift my load. Nothing remains to lift my load. Who can do that? Who can do that? Our aim was to lift the load. And now you are saying all the energy I have has been used to lift the lower pulley. And there is nothing has been left in me, no energy is left in me to lift the load which I intended to transfer from one point to some given height. That is not tenable. So these two, they go against the logic. There is no logic there. That's why we put now, we can put here, we can put here dash. And once we put there a dash, it's not attainable, it's not attainable, it's not attainable, it's not attainable. This one's so this one gives us the limit. It's not attainable. These ones, you can't. So your graph continues rising, but it reaches somewhere, it can't go beyond that. It can't. But remember, as I told you, we are only handling a small part of machines. What are machines? These are devices that help us to do work in an easier way and more convenient. So conveniency is there. It has limitation beyond which it ceases to be a simple machine but a complex. Okay? Now, that is what I wanted you to do. I want us now to look at more details. You will enjoy this. Look at more details. Effort to lift the load. Okay, when the load is, maybe I focus a bit, I don't know if I can get that focus. Yes, when the load is 100%, 50 goes to lift the load, 50 goes to lift the lower pulley. So I want us to concentrate on the load. I give you some arbitrary figure. So 50% of 1000. I have my energy I'm putting there, okay, 1000 joules. 50% goes to lift the load. That is the 50%, 50 of 1000. Then I imagine I've added the load, so there is more energy will be required. So I said, suppose the energy I put in is 1500 joules. So what is going to lift the load is 75%. If you can see here, 75% goes to the load and 75 goes to the lower pulley. So here I have lower pulley and here I have the load. So what is this? 75 of this. This is an arbitrary figure. I'm showing you. You increase the load, you have to have more energy. So 75% gives you that. And then the next is 86% gives you this. And 90% gives you that. So these are the effort required to lift the load. The effort required. Okay? Now, if I want to get load, I take a load, I divide by effort. Take a load, divide by effort. So I'll take the load is 100 divided by effort. An example. You should be able to get some figures now. Okay? Those figures are also known as mechanical advantage. Faida ya kimakanika. Faida ya kimakanika. Mechanical advantage. What do? You take the corresponding effort and the load. So it is load divided by effort. That's what you get, mechanical advantage. You will see. Now when you analyze this, you will find these figures are increasing. So they are increasing, but they don't reach somewhere. That's why I've put a dash, okay? If you compute this, that one you must compute this, and that. It does not reach 100%. It cannot, because we reasoned here, okay? That's why you will see the graph trying to stabilize. But the graph here, up here, that is the right representation. Just that. Don't tend to do this. This is wrong. This is wrong. There's too much extension, Too much extension. Because when the load become very, very big, things are not the same. But that is not for secondary. That is beyond secondary to analyze that. So yours should be just a small up to there. Should be there. It is understandable. You compute things up to that level. Beyond that level, it's not for you. So I want we move down, try to get the idea of that rising, and then it will stabilize. So you get mechanical advantage is load over effort. After that, I want you also to get, remember I'm dealing with the velocity ratio 3. I'm dealing with the velocity ratio 3. Our velocity ratio is 3, meaning that it means distance moved by effort over distance moved by load is 3. So our ratio dE to dL is equal to 3 to 1. Okay, that's very important. That's very important. How? I can get efficiency. Now. Efficiency is equal to mechanical advantage over velocity ratio times 100. Velocity ratio is 3. Okay, so if I divide all this by factor 3, they will still be increasing. Okay, they'll be increasing. just check here. We check here again. Suppose I have these figures were increasing. I'm just giving you a simple example. Suppose we have this data. We have 6, 9, 12, 15. And then each figure divided by 3. Each figure. So each figure divided by 3. Now, since these figures in black were increasing, 6, 9, 12, 15, if I divide it by 3, they will still be increasing. So what do you get here? 2, 3, 4, 5. They are also increasing. Okay? So mechanical advantage and efficiency, they give you the same graph. Mechanical advantage against load, efficiency against load, they give you more or less the same graph. Why? Because you see this is increasing, even this will increase. You have to interpret this correctly and you will see it. The load here is increasing. Mechanical advantage is increasing. It does not go beyond a given point. Okay? Even efficiency will increase. It will not go beyond a given point. That is the point. It reaches somewhere. It is like it is going to be flat, but you can't extend it to be flat. Just show that aspect of flatness. That is enough. That's enough. Okay? So I hope you are getting it. I conclude by saying, if work output over if work output is equal to work input, then we would get efficiency 100%. That's the only time. Because if this is equal to that, then it is 1. 1 times 100 is 100. But always our scenario is work output is less than work input. The denominator is always greater than numerator. Okay? And we have seen the reason behind that. Always the lower pulley and the friction come into play. So because they are there, you cannot say you cannot overcome them. And that's why work input cannot be equal to work output, and we cannot get efficiency 100% unless I just change something to suit my testing. Otherwise, continue subscribing, get more. Go through this, analyze. This, remember, these are my figures to explain. This is increasing because the load is increasing. Do it. I would like you to get efficiency from a different version. You see if you'll get the same figures. Which version? Efficiency is work output over work input times 100. So do for me work output here. Work output is equal to load times distance moved by load, and the work input is effort times distance moved by effort. So the efforts you get, you multiply by 3. Every time the effort you get by 3. And here it is by 1 because they are in ratio 3 to 1. And see, from work output over work input, you should be able to get the same answers as if I leave this over 3. Then you do or work out over work in. The figure you get here must equal to this. If this is letter P, even this will be letter P. I want you to work that and see. It's nice. Take your time. You have to reason logically. Logical reasoning. You are an engineer. You are a teacher. You are a doctor. You are a pastor. Logic You can't read the Bible well if you keep on jumping. See you, subscribe.